Let's begin. Today we will start on a new unit on one of my favorite topics ever, and Gauss used to call number theory the queen of mathematics, and I call differential equation. I think differential equations are the queen of mathematics, or king, or whatever, like the princess of mathematics. It's one of the greatest accomplishments that mathematics allows us to model reality and the world. And I'm very excited to teach you about differential equations. We will start with ordinary differential equations, and I'll try to teach them to you like you've never learned differential equations. I will not focus on solutions of ODEs. We will focus on just solving them numerically, but I will help you develop some intuitive understanding of what ODEs mean, how to build them, how to create them. We'll look at what's called compartment models, and they're very powerful. The next step is partial differential equations, obviously, after that, which will get us into more conservation laws and truly engineering science. I have this plot from XKCD. This is the guy I told you, he's a physicist. He left physics. He had a PhD in physics, something, and then he just does comics. He runs this website, xkcd.com. It's a really fun website. So I picked this from his website. It was quite a while ago he did this. And it's ranking fields by purity. You have sociologists right here. They're like depressed and like sad. And then you have the psychologists, and got like this goatee, no hair. And it's just applied sociology is applied psychology. And then the biologist says, oh, psychology is just applied biology. He's holding this this octopus or septopus, but if you know where the joke is from. Biology is just, so my son asked me, what's a septopus when we were watching Finding Nemo? And then we go through quintupus and tripus, and it was a good opportunity to teach him about these numbers. So biology is just applied chemistry, and then, which is just applied physics, and then the mathematicians are there, hey guys, how's it going? You all need math because you can explain. It's the language of the universe. It is the language of the universe. It is actually also the alphabet of the universe. Okay, the language and alphabet of the universe. So far we've done, if we plot the axis of where we're at, and I'm going to plot on the x-axis what we've done, and on the y-axis I want to plot your learning and knowledge in general. So we did some error analysis. We looked at algebraic equations. We did curve fitting and numerical integration. We pushed this within 1 month, which is fair. And then our next chapter is differential equations. And within differential equations, we are going to cover conservation laws and a bunch of other advanced things, but they all fit within differential equations. And if you were to plot on the y-axis your knowledge and how your knowledge is growing, it would look something like this. Once you hit these guys, your knowledge is going to grow exponentially. And not only that, your ability to do things, what you can do with differential equations is exponentially more advanced than anything you can do with all these are like little things that all will eventually kind of funnel into differential equations, because when we solve them, we need to compute errors. We need to compare our solutions to experimental data with curve fitting. We need to solve systems of algebraic equations because we're going to convert the differential equation to a system of algebraic equations. And I call these, and I got this this sentence from Dave Ramsey. Who knows Dave Ramsey? He's like this finance guy. Good for you, man. Good. You should listen to Dave Ramsey. You'll get your finances in order better. So he's got a lot of wisdom, this guy. And one time he was talking about people call his show and tell him all sorts of insane stories, like spending money and overspending and buying stuff. And one time somebody called. One phone call was like birth of a child, and the other one was the death of a family member. And he says this beautiful thing. He said, birth, like if you attend a live birth or go to a funeral, those are the tuning forks of life. So if you look at tuning forks, they have 2 rods, and you vibrate them, and they give this sound. So Birth and death are the tuning forks of life. Witnessing life starting and witnessing life ending, it will change you. And so I picked that up, and I think differential equations are the tuning forks of engineering science. We will start with ordinary differential equations. We'll talk a little bit about theory, like just classification and what we call them: initial value problems, boundary value problems, first order, second order. I'm not gonna touch on solutions or methods of solving ordinary differential equations. Leave that to the mathematicians. What I'm interested in is figuring out if a differential equation is linear, nonlinear, is it ordinary, or is it partial? Is it an initial value problem, boundary value problem, and how to best solve it numerically? Is it stiff or non-stiff? What is the best method to use to solve it? And we'll develop some theory along the way of interpreting differential equations. So we'll start by asking, what is a differential equation? It's not an activity. I will answer the question. As compared to an algebraic equation, a differential equation is an equation with terms that involve derivatives in it, or rates of change. So every time you see a derivative now, I want you to say the word rate of change. The rate of change of the population with respect to time, or the rate of change of temperature with respect to the location on the material. Okay, so when you think about it this way, it has a more intuitive feeling rather than just the derivative of temperature. Agreed? So a differential equation is any equation that involves derivatives of some unknown quantity. And a general, like I'm giving an example here. This is a differential equation. It has a second derivative here, second rate of change, or first rate of change, and it has a variable under the differentiation sign, and that variable, we call it the dependent variable. What is being differentiated against, we call that independent variable. That's something that we can control. We can control the material size if we're looking at variation of temperature in space. We can control time if we're looking at variation of pollution over time. We determine, I'm going to look at change of pollutant over 1 month, right? So you determine that would be an independent variable. Typically, time and space are your standard independent variables, because you have control over those, or they're given to you. And you'll all usually have a bunch of coefficients in front of these terms. These coefficients could be a function of the dependent variable and the independent variable. So this coefficient, the thermal conductivity, for example, here, could be a function, could change in space, and could also change as the temperature is changing. That would make it nonlinear. Same here, U, which we will later call advection. This term here also can change in space and as a function of temperature. Okay. All right. So why do we develop equations with rates of change in them? And I promised you that I will try to teach you and motivate you to learn differential equations like you haven't done before. And this is where it's going to start. And I'm going to claim that it is easier to describe natural laws and things that are complex in reality by finding relations between rates of change rather than going after a formula directly for the quantity of interest. And I want to motivate you with this example. Okay, so we're going to take a detour now. We're not going to learn about what I'm going to talk next. I'm just going to take a detour to motivate you for why we want to develop differential equations. So this is a motivating example. So we're not going to be learning about paramecium or lobsters. It's just a motivating example, okay, to learn about differential equations, why differential equations are useful. Okay, so we're going to start with a population of a unicellular organism called paramecium. This organism divides in half divides into two, like each one of these unicellular cells divides into two every hour or every 15 minutes, just typical cellular division. Okay? In this population, the individuals divide once per day. Okay, so great, that determines the rate of division. And so starting with a single individual at day 0, then we expect after 1 day to have 2, after 2 days to have 4, 8, 16, 32, etc. So you have this kind of growth of this population of paramecia, I guess plural of paramecium. Okay. So now let's start with a single individual, single cell. That's population P0. So it's 1 right now, but could be 10, and they can double in 1 day. But we're starting with the population P0. Okay, and then after 1 day, P1 becomes 2P0. Agreed? Because they're gonna divide in one day. And then P2 after 2 days, it's 2P1. So they're gonna double. P1 is gonna double. So we get 2 squared P0. Now my question to you, very simply, is what is the population of paramecia after T days have passed? So find PT, grab a paper and pen, and show me your skills. All right? So find me a general formula for the population after T days have passed, given that you have a P0 initial population. You can continue this by recurrence. So P3, do P3, and then you'll see a general trend. Okay. Give you a minute. Have a formula? Some of you have seen this before. Did I teach that when you were in my class? Yeah. The lobster, yeah, but not the paramecium. Yeah, I did this during COVID. Actually, you did see it. This is the first time I introduced this was 2019. Okay. All right. Any formula for those who have not taken numerical methods with me? Do you have formula in mind? Okay. Do you have formula? No? Yeah. So what do you think? Correct. Okay. So then, you could do P3, and then generally after T days, it's 2 to the power T P0. So, after 1 day, it's 2 P0. After 2 days, it's 2 squared P0. After 3 days, 2 cubed P0, and so on. Okay. This is an example where the quantity I'm after is the population of paramecia after T days. This is a simple example, right? They're just doubling. Okay, we did not consider that some other organism is eating them, or some of them are dying off, etc. We're going to consider that next. But this is an example where we are directly going after a quantity. And my claim is, it is easier to, instead of going after this formula directly, my claim is going to be, it is easier to develop a differential equation or find a relation for the rate of change of the paramecia population rather than the paramecia population directly. Okay, so let's see. Let's take this up a notch. So in general, organisms, I'm still going to focus on populations. In general, organisms do not just double. They might have, like when you go to mammals or lizards, other animals, right? They're going to date, they're going to get married, they're going to have a bunch of babies. Some of them are going to have 5 babies, some are going to have 1 baby, some 17, I don't know. Some will marry several other, individuals. So here's a population of lobsters, just, for the sake of illustration. I couldn't think of any other example but lobsters because they're really hilarious. They're like cockroaches of the sea. You're never going to eat a lobster again after this. So consider a population of lobsters, for example. They're not going to necessarily double, but they're going to grow with on a certain average. Like on average, lobsters can have, a population. Every pair of lobsters, a population of lobsters will grow at a rate of, 2 lobsters a month or 7 lobsters a month, something like that. So in general, the way we write this is not necessarily 2 to the power T P0. 2 comes from doubling. Okay. What if they don't double? What if every month they go by 1.1, okay, or by 1.2, or by 7.3, right? So generally, the general formula for a population growing uninterrupted, unfettered, is R to the power T. T is time. Could be seconds, could be hours, could be days, could be months. okay, times the initial population, right? So we can see this. Previously we had 2 to the power t because they only double, but in general there's a rate at which they're growing. So it's r to the power t p0. But since we like exponentials, we like to rewrite this as an exponential. So the way we write this, we say this is p0 e to the power lowercase rt, where the lowercase r is the logarithm of the capital R, and we call this lowercase r the intrinsic population growth. This is like a compound interest formula, okay? So this is common, and you can remember the exponential identities to go from this to this one. I didn't do anything here except just call capital lowercase r log r and write it as an exponential form because it's easier to work with exponentials. Their derivatives are easier to do, etc. So this lowercase r is an intrinsic population growth rate. Think of it as a like interest growth in an investment. Okay, so now we are working with this, and if you remember your exponentials, we have 3 options here. If small r is positive, then the population is growing. If small r is negative, then you have exponential decay. And if small r is 0, nothing is changing. Okay? So we have these like 3 options, right? If r is positive, there's more birth than death. If r is 0, there's the population is not changing for every lobster that's born. A lobster passes away, right? So equal birth and death. And then if r is negative, then the population is in decline, and you have endangered and threatened, etc. Okay. Now in reality, however, so we have the formula there, but now I'm going to go to reality, a more complex system, and I want to motivate you that it's easier for the complex system to write a rate of change equation rather than go after the population itself. So in reality, populations are bounded by available resources. There's predation going on. There's infighting, right? And so, they typically initially grow quickly, but then there's a balance that they reach. If there's no overpredation, there's a balance they reach that in zoology and in these population studies, they call this the carrying capacity of a population. It's just a number. It says, at most, a population of lobsters in this environment, in this ecosystem, can reach 5,000. Just because of resource. It can vary a little bit, but in general, it reaches this carrying capacity like this. Initially, there's exponential growth, but then as the population increases, the resources decrease, there's predation, etc. They typically reach a balance. And eventually, this is called, this is reached at k. So my question to you, find me the equation for this. So this is data observed, let's say, from an actual population. They're being measured over time, and then they look like this. Can you develop a formula for this? Just like we did previously. There's r to the power t, e to the power rt times p0. But then what? Okay, now if you develop an equation for this, you will teach the class, please, okay? I'm betting that you cannot develop an equation for this unless you're Chandrasekhar. So has anyone heard of Chandrasekhar, the great Indian physicist? He was one of 2 people who understood relativity. So the other one was Einstein, the other one was Chandrasekhar. And Chandrasekhar would come up with these formulas just out of the blue. It was like, oh, this is the formula for this. Like, how the heck did you figure that out? He's like the only exception to this. But since he's not here in this class, you all should not know how to do this equation, right? It's pretty hard. I mean, it's impossible. It's like, I have no idea how to develop an equation for this. I can hack it and say, oh, there's an exponential growth, so I have p0 e to the rt, but then I'm going to blend it with a constant k over here, and then how am I going to blend them together? It's going to be hand-wavy. It's not exact science. The actual formula is this. It's P of t, the population of lobsters, is k times p0, the initial population, over p0 plus k minus p0 e to the minus r times k times t. Okay? You go and plot this, looks like this. Okay? Put different values of k, different values of r, and you'll get this exponential growth and flattening out. Okay? That's a very complex formula. I don't think I could have even just kind of developed this just from looking at this. So here's an example where going directly after P is a difficult situation. Now I will argue that instead of going after P, let's go after the rate of change of P. And I will explain to you that it's actually easier to develop a formula or an equation for the rate of change of P, and then see what we can do with it. Okay? So first, I'll do a little warm-up. We're going to consider a population of lobsters with an initial size of P0. Now, the birth and death rates of these lobsters is equal, so that their population remains constant over time. Now, I want you to develop an equation for the rate of change of the lobster population over time. So dp by dt is equal to what in this case? 0. It's not changing. Okay, correct. So in this case, rate of the change of population of lobsters is 0. See how easy it is when you say rate of change of lobsters population. It makes sense. It's 0. It's not changing. It's flat. Then the solution is p of t equal constant. Because the initial condition is p0, then that constant is p0. Agreed? Okay, good. Great. Warm-up exercise. Now assume that the lobster population changes at the rate r. So that r times p, remember, when you need a bunch of lobsters to exist, like if you had 2 lobsters, if every pair of lobsters makes 1 lobster or half a lobster per month, but you have 8 lobsters, right? So it's going to be 0.5 times 8 lobsters. That's going to be your total new lobsters. So if your rate of change of lobsters is this lowercase r, and you have, at any point in time, you have p lobsters, then you're making r times p new lobsters, okay? At any point in time. If you have 15 and the rate is 0.5, then it's 0.5 times 15. Then tomorrow, you're going to have 25, that's 0.5 times 25, and so on. So we know r times p new lobsters are added or removed per unit time. R could be positive or negative, right? Now develop an equation for the rate of change of the lobster population p over time. So I'm giving you that r times p lobsters are created per unit time. So what is isn't that the rate of change of the lobster population? So what's my equation now for rate of change of lobster population? dp by dt equals, who said that? Yes, equals r times p, right? I'm giving you that. I'm telling you that my lobster population is changing by r times p per unit time. Now, what this does, this is the same variable here, okay? But at any instant of time, however many lobsters you have, as p is growing or decreasing, you're making r times p lobsters, or r times p lobsters are dying, okay? Now, what is the solution to this? It's p0 e to the rt. That's the problem we solved by hand when we did recurrence. Agreed? We did 2 to the power t p0, and we said it doesn't have to be 2, it can be capital R. Well, it comes from this, because I know that the rate of change of lobsters is r times p, and this is it. This is my governing equation. The solution to this differential equation is the formula we obtained earlier. Okay? I think this is easier to go after than... Now, it's intuitive to do the recurrence, okay, for a simple problem like this. Okay, so now let's complicate this. Now, what if the population cannot sustain more than a certain percentage of a given population? So at a point, it's going to reach k, so we need a switch. So far, what we've observed is the right-hand side tells you everything that's happening to the population. If it's 0, then nothing is happening to the population. If it is r times p, then the population is growing at that rate, exponentially, right? So now I kind of want to combine the two. I want a switch, some kind of a switch on the right-hand side, where once p is equal to k, So k minus p, right? Once p is equal to k, becomes 0, right? Because here, dp by dt is 0, agreed? But here I have exponential growth. Okay? So what do you think? Let's take that differential equation and replace r. If this r is there growing or dying, unfettered, uncontrolled. But what if we change this r into something that has a switch in it, such that when we reach k, it becomes 0. When we're far away from k, it's just normal growth. Can you work on the right-hand side for that? No? Okay, that's okay. That's okay. So if we had RP, this is our standard. This is unfettered growth, uncontrolled growth. But I'm saying now this growth is going to be controlled, is going to stop at k. So what if I change this r into r times k minus p? When p becomes equal to k, becomes 0. So I go flat. When p is much smaller than k, then I have just normal exponential growth. So think about it. Initially, with p0, 2 lobsters, and k is 1,000 lobsters, let's say. P is so much farther away from k that the population is just going to grow, uncontrolled. But as I approach k, as p approaches k, this becomes 0. So now within just one differential equation, the solution to this equation is, okay, so here I ask you, okay, initially when the population is smaller than k, then this term is almost k. So if p was 2 lobsters, and let's say the carrying capacity is 1,000 lobsters, this is a large number. It's almost 1,000. Okay, so you have almost something like r times p. So initially you're going to have exponential growth. But as you grow the population of lobsters, as p approaches k, so let's say k is 1,000, but p is 900 now, or 998. Then k minus p is a very small number. It's going to become a very small number. Or 999.9 p becomes a small number, then it's going to switch to 0, and then it will stay flat at 0. It will not grow anymore. If you solve this analytically, you get this solution. So that's how this formula was obtained. We developed a differential equation, and I claim it's easier. I know this might seem awkward to you, but once you saw the answer, you're like, yeah, it kind of makes sense. You'll get trained to the more you see of these, the more they become natural. And we will do an example together when we develop a model for the COVID pandemic. Okay, we'll do that together. We'll develop a model for that. We'll build all of these right-hand sides together. But this is the idea here, is that in these complex cases, you don't go after the formula. You go after a law. And that law is almost always expressed as a rate of change. Look at Newton's laws. Right? mdu by dt is summation of forces. It's all rates of change. All of it is rates of change. All the conservation laws are expressed as rates of change because it is easier to develop equations for rate of change rather than specific formulas. Okay. Now, this is my following conclusion, and you might disagree with it right now, but it is true, okay? I hope you'll get to agree with it eventually. I stand by my claim that it's easier to relate rates of change of quantities rather than going after the algebraic formula directly, the quantity directly. Now, notice that the solution of a differential equation is a formula, while the solution of a formula is a number. See how powerful that is? So differential equations generate formulas, and formulas generate numbers. Okay, that's a very powerful statement. That's why we use differential equations all the time. We can obtain formulas from them. They give us formulas that people use. Okay, let me add a couple of animations on this next slide. Okay. Okay. So formulas produce numbers. Differential equations produce formulas. Now, together, we cannot together built out this differential equation because this is a simple example. But there are systems that are even way more complicated. So do you know what produces differential equations? There's actually a thing in mathematics. So the answer to a formula is a number. The answer to a differential equation is a formula. But there's something, the answer to which is a differential equation. Do you know what that is? It's called calculus of variations, or variational calculus. Variational calculus develops equations that embody the physical laws, specifically the principle of least action. That's Newton's law, essentially. And those equations, like, they don't have derivatives immediately. They have like small changes. And you develop an equation. The solution to that equation, the answer to that equation, is a differential equation. It cannot be any more beautiful than that. Anyway, so if you have a chance, later on, you can take an extra course. Go take a course in calculus of variations. It is so underrated and rarely offered because nobody knows how to teach it. It's such a complex topic. But in physics, you might find a course like this in physics. So if you have an extra course you want to take calculus of variations. OK, so let's get into classification now of differential equations. I hope this exercise kind of demonstrated to you, motivated you to study differential equations. You'll get, with more practice, you'll get to learn how to appreciate them and build them by yourself. All right, so there are two flavors of differential equations, ordinary and extraordinary, or partial. So we call them partial, not extraordinary, because what's ordinary about an ordinary differential equation is just has ordinary derivatives, or the lowercase d, not the partial, because your dependent variable only depends on one independent variable. Yeah. So an ODE is a differential equation with only one independent variable. Means an ODE can only contain ordinary derivatives, hence the name. So these are some examples. This is one example of a population growth. It's called the logistic equation, by the way. If you want to look it up, it describes population growth. It's a very nice, interesting equation. Rate of change of water height in a tank. So when you study fluids next semester, or maybe we touch on it in this course, you're looking at the change in height in a tank. There's water coming in, water flow coming in, water flow coming out, and the area. And so you look at the rate of change of the height. So we're looking for the height, but it's easier to develop a differential equation or for the rate of change of the height. This is called the advection diffusion equation. It describes heat transfer or diffusion and advection, things that are moved by an airflow. We're going to talk about this more and more as we go through the semester. This is, note here that this differential equation, this ODE, is a function of space. This is something changing in space rather than something changing in time. So we're going to make that distinction in a bit as well. And finally, a chemical reaction, concentration changing based on some source term, one of the simplest ODEs. Now, contrast that to partial differential equations is one where it's a differential equation, but the dependent variable, or you have more than two or more independent variables. And typically, those are space and time. Other exceptions exist, but space and time are the typical ones we're going to be dealing with. This is, for example, the heat equation in 2 dimensions on a disk or a plate or a door. There's temperature changing both in x and y directions, in two directions. This is a time and space equation. You have time and space, and this is the unsteady heat equation. So when there's no more change in time, you get the steady state heat equation, whose solution was just a straight line. But adding a time derivative allows you to see how the temperature is also changing over time from an initial condition. And so these are all partial differential equations. This is a unsteady, so contrast this to this one. This is an unsteady version of the advection diffusion equation. And we will learn later that this term describes movement of information when there is a flow. So for example, if I put an incense stick over here, just gonna nicely gonna come out and just gonna make these beautiful vortices. It's gonna take a minute for you to smell it, right? But if I put a fan over here and blow on the incense concentration, you're gonna smell it faster, right? What's happening? The airflow is grabbing that concentration and moving it quickly to you. So that is described simply by this term. Okay? U is the speed of the air, and this rate of change, first derivative, first rate of change for temperature or concentration, is going to describe that. This term describes the change if I didn't have airflow. It's just as it's slowly diffusing, like a drop of ink in a cup of water. It slowly diffuses. Then you come and stir it. It's going to diffuse fast. It's gonna transport faster because you're moving it with the liquid, with the speed, with the velocity. Okay, advection and diffusion. We will talk about that as well. All right. We're gonna in these few lectures now. We will only focus on ODEs. We will leave PDEs for later. Okay. So we will start by classifying ODEs themselves. If you remember, I showed you ODEs. Some of them will have with time, some of them with space only. Okay? So they come in two flavors, ODEs. Propagation problems, which we call initial value problems, and equilibrium problems, which are called boundary value problems. Again, I'm talking only about ODEs, so there's only either time or space, okay, one of them, not both together. If you put both, you have a partial differential equation. For initial value problems, you are given the initial state of the system, so an initial concentration in a tank of two reactants, and go, start reacting with each other, right? So you're given the initial concentrations, and say, go, start reacting, what's going to happen in time. So this would be this example, a well-mixed reactor system, or a tank. This example I gave earlier, there's initial water in here, and suddenly I have water coming in and water leaving. What's happening to the height of water? This is an initial value problem. Okay. Now, there are other examples, population growth, pandemic, disease spread, for example. You have an initial condition, a certain population, half of it, there's like 2 infected persons, the rest are healthy, for example, and then go, interact, see what happens in the system. That's an initial value problem, an initial condition problem. Now contrast that with equilibrium problems, where we call them boundary value problems. In those cases, you are only given the conditions at the boundary. You don't care about the initial state of the system. What I care about is at equilibrium, given the conditions at the boundary, what is going to happen inside those boundaries. A classic example is the heat equation that we did earlier. So this is an example of the wall where you have sheetrock, insulation, plywood, and siding. Outside temperature is 10, inside temperature is 70. Show me the change in temperature in the middle, because I'm fixing the boundary here. What is happening inside? This is the differential equation in this case. It needs 2 boundary conditions. We'll talk about the number of boundary conditions as well. And go, see what's find out what happens. Now, obviously you might think, well, the initial condition in the wall matters. Eventually, if the boundary is fixed, you're gonna reach steady state, and the time component doesn't matter anymore, okay? If you wanna add a time component, you're gonna have a partial differential equation. Okay, so because we're working with ODEs, we're going to kill the time term and say at steady state, at long term, what is happening inside this wall. So these are called initial value problems, or IVPs, and these are called boundary value problems, or BVPs. We will learn how to solve both of them. These problems obviously require an initial condition. These problems require 1 or more boundary conditions. Now, further classification of ODEs is a first order ODE is in terms of order. So the order of the derivative, you've seen first derivative, second derivatives, you're going to see third, fourth derivatives possibly. A first order ODE contains only the first derivative of a dependent variable, or the highest derivative in the equation is a first derivative. Okay? So you can have a single equation, dphi by dt equals some right-hand side, so start getting used to this nomenclature. Phi is a dummy variable that I will use from now on to describe temperature, pressure, velocity, position. It's just a dummy name for a variable, call it phi. And there's a right-hand side. I don't know what the right-hand side is, but I know it's a function of time and phi. It doesn't have space in it or anything else. At most, it can have time and the dependent variable. Okay? Or you can have d phi by dx equal right-hand side, some x and phi. So this is another ODE, first order as well. And you can have a system of first order equations. We will also learn how to solve systems of ODEs. And you write this as d phi by dt. Again, the same thing, but in this case, phi is a vector. And the right-hand side is also a vector. So you have equation 1, equation 2, equation 3. We'll get to that later, how we kind of put them together as an array in Python. A second order ODE contains second and possibly first derivatives of a dependent variable. Okay, so the highest derivative in a differential equation tells you whether it's first order or second order or third order and so on. So for example, this is the advection diffusion equation again in space. It has a second derivative for the concentration of something and a first derivative. So we call this a second order ODE. This is called the diffusion term, as I explained earlier. It describes how things propagate at the molecular level. It doesn't necessarily mean it's slower than convection where air is blowing, because you could have very fast diffusion compared to slow convection. So what matters is the ratio of U over K. You'll learn that in mass transfer. This is the classic example from the cartoons where someone is baking a pie and then the concentration kind of propagates. If there's wind, it's going to bring the concentration to Mickey faster. And so if you are to plot, for example, the concentration of the food smell, and there's an apple pie over here, and there's kind of wind blowing on the apple pie, that concentration downstream of the apple pie is gonna immediately pick up because you're propagating it faster. A system of equations could be like a pandemic, which we will derive this system together in class. This is an example when COVID started, I put together this system. This is a known system called the SIR pandemic model, but then we built on it because I wanted to add the impact of social distancing, if it makes sense or not, or what if you only distance the risky populations, the elderly or the compromised. And so I did a little study on that based on this system. So what we're looking at here are three populations. Susceptible, so these are the healthy population who have not been infected yet, in blue, infected in red, right? So blue is, and then recovered with immunity, those in green. So initially, this is a percentage, okay? So like a fraction, or let's say 1,000 or whatever you want. This is a percentage. Almost like 99% of the population is healthy, but you have like one or two infected over here. Okay? Now they interact with each other. So the symbols here, S for susceptible, I for infected, and R for recovered. You will see later that the rate of change of the susceptible population depends on the interaction between the infected and the susceptible. And it's a product, because I have to have contact with an infected person, okay, to get infected. So naturally what's going to happen, this susceptible population is going to decrease while the infected population is going to increase, right? Because you're moving people from blue to red, right? They're becoming infected. And the more infected, the faster you're going to infect the entire population. Again, they all become zombies, right? And then, you reach a peak, and this is what they call during the pandemic, like the maximum capacity for beds in a hospital, for example, because they do similar studies for influenza, for instance, like how many beds do they expect this year. But then eventually people are going to move from red to green, where they are recovering with immunity. And then, so you see most of the population here has become infected, and then the infected start getting recovery, say 14 days, and then there's no more infected, and eventually you achieve population immunity. We will derive this system together. It's a lot of fun. It's very easy. And I will ask you as a bonus project or a bonus problem to add, for example, deceased or add social distancing if you want. Okay. So why do we use numerical methods to solve ODEs? Obviously, because we don't want to do analytical solutions. They are perceived as hard, or sometimes we forget how to do an analytical solution. For most systems, these equations are nonlinear, they're coupled, they're hard to solve analytically, and the analytical solution usually is rather complicated. In some cases, in other cases, you cannot find it in closed form. So there is some kind of numerical procedure going on. And because this is also about tools for engineering science, I want to give you an ODE, and you have 1 minute to code it up. Literally, that's what we will do. We have an ODE. In 1 minute, we can code up a solution and see the answer. If you're probably not taking ODEs concurrently because that's a course you took in undergrad. But if you're taking an ODEs course or a differential equations course, this will be very, very handy. We will start with initial value problems. Let's resume. Next, we are going to cook a lobster. And if you are a vegetarian, you can cook an eggplant. Okay, the same principles apply. Okay, we're going to have the same equations. But I like to keep the lobster for historical purposes. We even have T-shirts with lobsters. They all sold out, or like students took them. We had some lobster 3D printed things at 1 year for like student awards. All right, so let's imagine this insanely fictitious scenario that a recent report that I made up found that the population of lobsters is growing out of hand, and that those lobsters are like eating everything at the ocean floor, disrupting global ecosystems, like causing tsunamis and whatever lobsters cause. Okay, so it's a made-up report. The WHO and the CDC are recommending that it's open season on lobsters, so people should start eating lobsters as snacks, like in the morning, you're like eating baby lobsters, you know, and you kind of fry them, or eggplants, okay? Imagine the same story for eggplants, as snacks throughout the day to help control the population. Now, in this imaginary story, you are an engineer for a food company, MacLobster, let's call it. It's a startup, and you are trying to find the fastest way to cook these lobsters. These lobsters come in, Maine lobsters, right? You want to cook them real quick. It's a fast food, MacLobster. You can't wait 20 minutes to cook a lobster. Oh, sir, wait for the lobster. No, I want lobsters ready, crunchy, delicious. I want to eat them real quick. And you have two options. You can boil it in a liquid or bake it in the oven. Okay, you have two options in your facility because the EPA said you can only boil or bake, okay, nothing else. You can't, like, you know, shoot it with a laser or something. Darn it. Okay, any of those cool stuff, right? So you have two options. That's what would happen if I forget it, like baking. You bake it in the oven or boil it in water, or you can boil it in oil, okay, or you can air fry it. Well, you boil it in air, I guess. Okay, let's get the giggles out. This is a serious course, please. Okay, the assumptions is that, and you know, this, you might not know how to do this, but I'm hoping you have an idea of how to do it from heat transfer. If not, Professor Sutherland will teach you how to do it, okay? We assume that the lobster is a cylinder, okay? Simplest assumption. It's a cylinder, and you know, we're gonna assume it's got a typical length 30 centimeters and a radius of 10 centimeters, just on average, kind of capturing the claws, etc. And it remains at a uniform temperature. So, you know, when you dip it in the oil or in the water, or it was at room temperature initially, and then you put it in, obviously, you know, it's gonna probably heat up faster at the surface than the inside, but assume that it just heats up equally. Otherwise, we have a partial differential equation. You have to look at how temperature is changing over time and space, right? So we don't want that. I'm gonna assume that it just cooks evenly at the same temperature, so it's just like the whole thing is 1 point essentially. And that the lobster's main mass remains constant, no relativistic effects, and the heat capacity of the lobster is approximately that of water. That's a reasonable assumption because most of the tissue, most of the contents is water inside the lobster. And if we put these properties, L length, radius, The surface area of the lobster, we're going to need that for the heat transfer equation. Mass, say 1 kilogram, that's a heavy lobster. It could be like, we're going to change these numbers once we develop the governing equation. And the heat capacity, this is how much energy do you need? So what is the heat capacity? What is the heat capacity? Yes? There is 1 kilogram by 1 degree Kelvin. You can tell from the dimensions. It's energy per mass per temperature. How much energy you need per unit mass per unit temperature. So how much energy you need to raise the temperature of 1 kilogram by 1 Kelvin. So for water, you need 4,200 joules to raise the temperature of 1 kilogram of water by 1 degree. That's a pretty useful property, right? Okay. So this is the description, because this is like serious stuff. You're designing your company, you're getting diagrams of lobsters, their dimensions. You want to study all of this seriously. So you have these properties of the lobster, and you have two options. You want to boil it in a liquid, or you want to bake it in the oven. Now, this hits spot on when we did this in your homework, where you had dt by dx, right? And you had something like this, t minus t infinity. Right now, we're doing this in time. We're looking at the temperature of the lobster as it changes over time, as it's exposed to a boiling liquid. A boiling liquid is called convective heat transfer, if you remember from your heat transfer. H here is a coefficient, is a heat transfer coefficient. It tells you how effective that liquid is in transferring heat from the liquid to the lobster. Okay? The larger the H, the faster the heat is going to be communicated from the boiling liquid to the lobster. A and M and Cp, they're the properties of the lobster. T is the current temperature of the lobster. It's the same T here. T infinity is the boiling temperature of the liquid. So what happens when T approaches equal T infinity? Goes flat, right? Initially, when T is much smaller than T infinity, when we start cooking the lobster, so you boil the liquid, that gives you T infinity. That's the boiling temperature of the liquid. It stays constant as it's boiling, right, during phase transition. Initially, the temperature of the lobster is far away from T infinity. So there's a large difference here. This is going to grow fast. So it's going to go quickly, but then as T approaches the environmental temperature of the liquid, or the boiling temperature, it's going to stay flat. Radiation, similar, rate of change of temperature of the lobster, but on the right-hand side, you have something quite different. You have a T to the 4, that's also in your homework assignment, but we did it in space. Okay? You have a T to the 4 over here and T infinity to the 4. T infinity is the oven temperature, radiative temperature in the oven. So that's, say, broiling or whatever, 450 Fahrenheit, right? And again, same thing. As T approaches to infinity, you're going to go flat. It's not going to change anymore. But initially, you have a big difference over here. So it's going to heat it up pretty quickly. There's a bunch of coefficients here. Sigma is the Boltzmann constant. That's for radiation. It's a very small number, relatively. Epsilon is called the emissivity of the radiation environment. So are you blocking the radiation somehow, or all the radiation is coming and hitting the lobster? We're going to assume it's all coming and hitting the lobster. You don't have like smoke in there or something so that's going to absorb the radiation and not allow it to transmit to your object in question. And A and M and Cp, they're the same thing. So these equations look the same, rate of change, but the right-hand side is changing because we're changing the mechanism of how we are heating the lobster. Okay? You should have done this in heat transfer, also for conduction as well. But if you haven't, these are the governing differential equations for these two methods. And we want to solve this. We want to solve this numerically. Now, obviously, this is a linear equation. You can solve it analytically, but we're not going to do that. We're going to do it numerically. I will describe the general strategy of how to solve differential equations, because this is not a course on numerical methods. I don't want to get into the weeds of numerical methods. I just want to give you the tools. You probably know it. You probably know ODE int. I'm going to teach you something different in this course. something a little more powerful, also in Python. And the general strategy is like we did in space, where when we did in space, we took our space domain or the material and we put points on it and we tried to solve for the temperature at those points. We will do the same thing here from some initial time to some end time, t end or t final. And this is the profile we're trying to capture. We're trying to solve. We only have the initial condition and we have an equation for the rate of change of this property. We're trying to find the red curve. Could be temperature or something else, but in general, we're trying to find this. So what we will do, similarly to what we did in the spatial approach, we're going to split this into points, bunch of points, and we're going to call the distance between these points a h, or delta t, a time step size. So from now on, this is called a time step. Okay? This is how big, because we're moving this in time. We're going to start from t0. We have the initial condition. We're going to take a small step, figure out how to compute the next value. Then we're going to assume that's our new initial condition. We're going to take another step and so on until we reach t end. Okay? So we say we divide the interval into smaller intervals in time. We call that our time step delta t. Okay? And now our purpose is to find, so we only have phi 0. And we have d phi by dt equals something, right? Now from that d phi by dt, I'm going to figure out to find a formula to go from phi 0 to give me phi at t1. And then from that to give me phi at t2, and so on and so forth, to complete recursively that solution. Your solution is going to be discrete only at these points. It's not an analytical solution. It's only given at the points of your choice, or whatever Python is going to decide. We will see that in a minute. Okay. I haven't decided if I want to teach you how to get this. I might just cover it very briefly, but I want you to drive first before you learn how the car, what's going on inside the car. So we will learn the tool in Python. As long as you exercise common sense about what you're doing, we will learn how to do this in Python blindly without knowing what's going on inside Python. Just the tool, hey, it's like a calculator. Solve this differential equation for me, how to do it. So we start with Python. And from scipy.integrate, so now we're mostly working with scipy, not numpy anymore. Numpy is still there for arrays. But from scipy.integrate, we are going to pick up a library called solve IVP, or solve initial value problem. If you are using ODE int, or if I taught you ODE int, forget about that. Don't use ODE int anymore, okay? Especially for serious work. ODE int is obsolete, is not very powerful, is not as powerful as solve IVP. So solve IVP in general solves an ODE of the form d phi by dt equal to a right-hand side, whatever the right-hand side is, it doesn't care, of the form t comma phi, and later we will add arguments over here. But the first two arguments in your right-hand side always are independent variable comma dependent variable. Okay? Always. This is what it looks like. I'm going to store my solution in a variable called sol. This is the best name ever. And then solve IVP, at a minimum, solve IVP requires 3 arguments, otherwise it will not run. But it requires at least 3 arguments. A right-hand side function, you kind of know now what this is. It's like when we did with fsolve. A t-span, I don't know what that is. And y0, oh, that's probably the initial condition. So let's see what those are. The right-hand side is a Python routine, like we did when we did the root. It's just a callback to a Python routine that implements your right-hand side. Our right-hand sides, in this case, we have 2. One for convection, t minus t infinity times something, and one for radiation, t to the 4 minus t infinity to the 4 times something. So each of those is different right-hand side. Always your right-hand side with solve IVP, at a minimum, needs 2 arguments, and they are in this order, t comma phi, independent variable, dependent variable. If you switch those, you're going to mess things up. Because internally, solve IVP is calling RHS, and by definition, it's giving it t comma y, independent comma dependent variable, because it's moving every step. And at each step, it's going to give me the current time and the current value that I have to predict the next value. And it's going to send them in this order. Don't mess this up. Y0 is your initial condition. We have one ODE here. So we have one initial condition. You have to provide it as an array or in parentheses. I always put it as a list, like a bracket or a NumPy array if you want. But it has to be as a list or an array. Okay? Because later when we go to systems of equations, we have to provide a list or an array of initial conditions. Tspan is simply a float or an array of 2 times, your initial time and your end time. Where do you want to start? Where do you want to end? You might say, aren't we always starting from 0? Not necessarily. You might pick up a condition where you're starting from 1 minute of a situation where you've achieved a certain reaction, or you're picking up from a previous solution and you want to continue the solution. You may be starting from a certain, or your right-hand side depends on time, and the absolute value of the time is important. So you need to give it the T0 and the T end. Okay? Now, what this does, it solves the system and it returns a lot of things that you're going to store in this variable sol. The most important things you want to get out of sol is sol.t. This gives you the time points at which the solver decided to find the solution. Here's a trick here. Remember how I told you we're going to take the time domain and put points in there? We didn't specify that here. All we did was give it T0 and T end. Why? Because solve IVP tells you, no, leave that job to me. I will decide how many points you need. How? It's a miracle. It's basing it on stability considerations and its need to try to find the solution. Internally, it does some really advanced calculations to figure out what that interval time step needs to be. So you will see on some light problems, it will divide the interval into 4 time steps. On some more complex problems, it's going to divide it into 1,000 time steps. We will have control over this later. I'll show you how to overcome this. But as it is, you just give it the beginning time and the end time, and internally it figures out how many points it needs to do. So then when you come to plot, you want to plot the solution versus the time. You need to get the time points from what the solver did, so sol.t. That gives you the time points at which the solver found the solution. And sol.y is actually the numerical value, the numerical solution, your numerical solution. So you're going to plot sol.y versus sol.t. Okay, so let's do this together in class. We're going to boil or bake Mr. Lobster in Python, okay? No lobsters have been harmed in this class. Should put that as a disclaimer. Okay, so I will move this over here. We have 15 minutes, so hopefully we'll get at least one of them. Okay, so let's open up, oops. So go to your favorite, whatever you put your Jupyter notebooks. And let's create a new notebook. Window, move to Creston. And let's call this Fall 2025 Lobster or Cooking Mr. Lobster. Okay. So we will get a bunch of boilerplate in as usual. So you can copy those from your previous notebooks. We have the boilerplate, but I also need from scipy.integrate import solve IVP. Okay, so execute this. The first step is to define the right-hand side. So let's define so we'll do the convection first so we can get a solution before, because maybe the time hopefully we will end just on time. So boiling it in a liquid. Let's do the boiling it in a liquid. We're going to define the right-hand side boiling, right? And by definition, if you remember, I need to provide T comma phi. So I'm going to assume that this is given T comma, what is my phi? It's temperature, okay? So it's temperature. If you're concerned that the symbols are T and T, put time and temperature, or time and phi, okay? But this is T and T, time and temperature. And let's program a bunch of things here. We're going to put H is, let's see, what did we put? H was 500. I'm going to not put the units here for the interest, just so that we can just get this done in time. L is 0.3 meters, R is 0.1 meter, and the area is 2.0 times mp dot pi times R times L plus 2.0 times pi, right? So what is, yep, pi r squared times np dot pi times r squared. So that's the surface area. Frankly, if you want, you can just lump all of those into a coefficient, call it alpha, okay? But I'm trying to be quite realistic here into how these are derived. M is 1 kilogram, and heat capacity is 4,200 joules per kilogram per Kelvin. And okay, so now I have all of these properties here. I'm going to execute this. I'm making them global. It's a bad idea to make them global, but I'm making them global for the sake of illustration of this problem. And for here, I'm going to need T infinity. And let's put T infinity at, I don't know, boiling temperature of water, 374 Kelvin. And that's, you know, standard conditions. And finally, all I have to do is build the right-hand side. So right-hand side for boiling is equal to minus H times A over M over Cp, right? So that's HA over MCP times T minus T infinity. Again, remember what we did with nonlinear solvers. You just assume that there's a value here. As far as you're concerned, you have access to time, to the independent and dependent variable here. How? It's none of your business. Python figures that out, okay? But assume that you are given this info. So all I have to do, if I have this info, I just build the right-hand side. Minus HA over MCP T minus T infinity. I got my right-hand side. And what do? I simply return it. Return right-hand side. Done. So next, we will do solve IVP. And I'm going to do T0 equals 0. And T final, let's see, let's run it for 20 minutes, let's say. 20 minutes times 60 seconds. Because the dimensions in this ODE are per second. So I need to convert that in 20 minutes expressed in seconds. Okay? So that's my T final. And then finally, I'm going to do solve my, okay, my sol with boiling, solution with boiling is equal solve IVP. Now, you open parentheses, press Shift Tab, and you'll get the function signature. You see here, it wants at least these three things. There's a bunch of other things here. We'll talk about them later. But this solves this right-hand side, T-span, and Y0. So let's do this. Solve IVP, and I have my RHS boiling. And then I have my T-span, which is T0 and T-final. You can put them like this. And my initial condition, okay, so what is my initial condition? Room temperature, T0, let's say 305 kelvins. Initial lobster temperature. And again, I have to put this as an array, so I put it in brackets, T0. Good, it didn't throw an error, but it did something. Now, if you print sol boiling, this is going to give a bunch of things, okay? But look here, there's this, it's got a bunch of things, and there's this T here that I said contains the time points, and Y here, it contains the solution. So if I go and do plt.plot sol boiling dot T, I'm plotting Y, the solution versus T, and then sol boiling dot y. And just, if I just do this, and then do it OK, like we did. I'm not going to connect with dots. Oops. Sol boiling. Oh, sorry. Sol boiling dot y 0. My bad. So this is a mistake I forgot to put here. Let me fix this here. Sol y 0. Okay. So this is what this is giving me. I'm going to connect it with a dot. And let's put plt.grid. It solved it, and it solved it. It picked its own points, a few points here, and then more points here, only one, kind of. It picked its own time points. It's not, doesn't look perfect because it looks like it's jagged, but it did it. It did solve the system. And indeed, how can I check? Well, when it reached my T infinity, which is 375, so it cooked it. So on the x-axis, I have seconds. Let's convert that into minutes. So let's divide by 60, okay, by 60, so that we have it in minutes. Okay, so in 2.5 minutes, this is a little unrealistic, but in 2.5 minutes, we reached our boiling temperature. Now, that's not I want it well cooked. Okay, I don't want it to be, so don't boil it in water. But maybe, put it in oil. So if we were to change in oil, we can push our T infinity a little higher, and then H is going to change. And we can look at all of those options. Let's see. So we have 5 more minutes. Okay, so let's do radiation, shall we? Let's do radiation. Define RHS radiation, time T. And in this case, for the radiation, I have these properties here. I need to put in my sigma. Okay, so sigma is 5.6704 e to the minus 8. Oops, e to the minus 8, right? And my epsilon, the emissivity is 1. Epsilon is equal 1. And otherwise, my right-hand side is equal to minus sigma times epsilon times A over MCP times T to the power 4 minus Tn to the power 4. What is Tn for radiation? Let's say, I don't know, 400, 450, 500, 450 for broiling, let's say. Okay? So that's my radiation, right-hand side. So again, what I can do here is solve radiation is equal solve IVP. Can be any easier. It will take you 1 minute to program this if you don't have a lot of numbers to type. RHS radiation, and we'll give it my span, T0 and T final, and my initial condition also at the same temperature. That gives me sol radiation, and then it crashed because I made a typo here, epsilon, epsilon. Okay, there you go. It did it. So let's plot this. Now, the time points for radiation might be different than the time points for boiling because it's a different differential equation. So I need to use the time points for radiation here and the y points for radiation as well. And let's say in red, oh, it's still solving this. What is going on here? Oh, it's taking a long time to solve it. Epsilon. Let me kill the kernel. It's been giving me some trouble. My Python probably needs a full reinstall. It's kind of stuck with the radiation solution. From T0 to T final, it is getting stuck. That's. Did I make a mistake here? Minus sigma epsilon A over MCP T to the power 4 minus T infinity to the power 4. No, that's correct. Right? Yep, this should be correct. sigma. Okay. I don't know why it is being stuck here. Well, that's a question for next time. I guess. Hold on. Okay. Anyway, we'll get this sorted out. So it seems to be stuck over here. Oh, I'm not returning the right-hand side. Of course. Return RHS. So it's stuck. It's like waiting for the. Okay. So with radiation, kind of looks really crappy, right? It's just got these points here, and it's hitting, but it's kind of finding a solution, but that's not what I would like from this solution. I want more points. I want it to look smoother. It looks like a bunch of straight lines connected with each other. However, for radiation, it takes it, 12.5 minutes to reach the same temperature as boiling. So I would rather boil this than put it than bake it. Right? So it's taking much longer to transfer this radiation through the object and bake it in these settings. Because I'm using this H value, this temperature, etc. We can play around with the size of the lobster, with the parameters. We'll do some of that next time. But focusing on what matters here is that we got a solution, right? Well, what matters is the physicality of the solution. But we did get a solution. It's not perfect. Like the way it picked the time points for radiation, it picked 1, 2. Looks like it picked only 4 points. I don't like that at all. So next time we will talk about ways to solve IVP to solve the solution at more points that it wants to do. Okay? And we'll talk about systems and other things. A lot of exciting stuff going on. Okay? Go home now if you have an ODE that all your life you wanted to solve since you were a kid. Okay? Go and try and solve it with this. Okay, or something you've seen in another course. Okay, I know some of you are taking advanced numerical methods. You're probably going to be touching on those at the same time. So try to run it with Solve IVP. Okay, thank you. Godspeed. I'll see you on Thursday.